Hello, 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 everyone. If you're watching this, you missed day 1 of our week 6 lecture in computer science principles. Let's get to it. So we did a short warm-up, which I'll show you in just a second. And then we moved on to our new unit, which is going to be the internet. Woo, the internet. So we're going to take all that stuff we talked about in terms of digital information, and we're going to now see how it's being transmitted through this worldwide network. We played a little bit with the Internet Simulator, and there is an assignment that we started called Wire Connections. It's going to be due Wednesday by midnight, along with your journal, which was supposed to be due last week, but I messed up on the due date, so it is also due Wednesday. Keep in mind that your assignment from last week on ethics of digital information is due tonight at midnight, so do not forget to turn that in, please. By the end of this lecture, I hope that you can identify paths connecting two devices in a simulated network. You can explain how computing devices can be connected to form a network in the first place, and you can use this internet simulator to communicate information with a partner. Very, very basic ideas that hopefully won't be too difficult. So for our warm-up, what we did is we navigated to modules inside MIME-CPS, and then there's a virtual poster for you guys to check out and post some answers to what is the internet and what questions you have. So please make sure you do that if you weren't in class, so I can review your ideas, and if you have a pressing concern, I can try to address it in our next class lecture. We then watched this short video. Please go ahead and check this out on your own. It's inside the slides for the week, where Vint Cerf, who is one of the creators of the internet, goes over some interesting fundamental ideas behind the system. Next, we looked at the Internet Simulator. The Internet Simulator can be found on code.org. So let's navigate there together right now. Code.org, underneath Unit 2, which is now available to you. You'll see that the first lesson has a widget called the Internet Simulator. If you open it up, you'll find yourself in this lobby. Now, you won't have anyone to connect to. Oh, apparently there's some people hanging out in here still. But if you don't have anyone, all you need to do is copy and paste this URL into a separate tab, and you'll be able to connect to yourself. So if you want to ever play around with one of these internet simulators on your own, just open up 2 separate tabs, and you can join yourself and accept the request from yourself. Sounds kind of lonely, but it's okay. And then you can play around with this tool and see how it works. Essentially, any ASCII or regular plain text you put here, like "Hi, how are you?" is going to get translated into the binary representation down here using the ASCII codes. So H is this 8-bit 1-byte code down here, and so on and so forth. If you hit enter or send, the message gets transferred. Please note how it gets transferred, 1 bit at a time. And then you'll see it arrive on the other screen here. So very, very basic, straightforward idea. We're sending 1 number at a time, and then it gets translated. But this brings up a lot of questions. For instance, how does the computer know when the message is over? And then, do any of these numbers ever get lost on the way to my other computer? And then lastly, how do we expand this? Currently, this is just 2 people talking to each other, but how do we get more computers connected? And then, as a result, how do we know who communicates with whom? So all of these questions will be answered in following lectures. Today was just an introductory to these ideas. So I spent a long time in class coming up with these questions, and I'm just giving you an overview of them here. All right. So how is it similar and how is it different from the internet? Obviously, the main difference from what you just saw is on the internet, you have millions of possibilities as to who you could send information to, not just one. We finished watching that video, and then we went on to do this short assignment about building a network. So a fundamental issue that you need to consider when thinking about adding more computers to the internet would be, how do we physically connect them in order to make the network redundant and resilient? One of the things Vint Cerf talks about in the video that I didn't show in this lecture, but that you should watch, is the idea of the internet being a direct descendant of the ARPANET, whose primary concern was to make sure that military information wouldn't be lost in the event of a nuclear strike on one data center, thereby distributing the information throughout a mesh network and creating a lot of resiliency. The internet functions similarly. If you take out a small part of the infrastructure, it shouldn't necessarily affect, at least in large part, the rest of the network. So how do we achieve this? Let's go ahead and take a look at the assignment that you guys need to do for me. So underneath week 6, the assignment is posted right here, called Wire Connections. Let's open it up and see what we're working with here. The assignment looks like this. It's a PowerPoint. There is a group. We worked on this in groups, but if you work by yourself, that's okay. You need to figure out how can we connect these 5 nodes, pretend they're computers or people or whatever you want, and you can draw lines among them, like so. For instance, that would connect B to A. And I'd like you to connect them in such a way that each node can speak to every other node directly. There's only one way to do that. But then for challenge 2, what is the least number of lines we can draw so that everyone can talk to everyone else successfully? Hopefully you draw a lot fewer lines on this one. Following that, I'd like you to make sure that we still try to have few lines, but the network can still function if we cut one of them. How can we accomplish that? And last but not least, I'd like you to put all of that together. So try to make a cheap, resilient, and redundant network. How can you do that? And it's up to you to figure that out and then answer a couple of questions on the end here. So hopefully that's not too bad. Please email me if you have any questions about the assignment. That was the end of our lecture. Oops, sorry about that. That was the end of our lecture for the most part. Now there is one more thing, which is this vocabulary that you guys should be familiar with. So computing device is obviously just a single device. Could be a computer, a phone, a tablet. A computing system occurs when you have multiple devices that are working together for a common purpose. This could be like a mainframe at a bank or several computers solving one problem together. And a computing network occurs when you have a group of interconnected computing devices that are sharing data amongst themselves. And you could have various size networks that engulf smaller networks inside themselves, creating larger and larger networks. And it can be hard to piece those apart. A path that a packet takes through a network is an important concept. So to get from this computer to this computer, how do we do that? The information must take a path through the network. And last but not least, the idea of bandwidth as contrasted with latency. So bandwidth is how much data you can send in a given amount of time, whereas latency is how long it takes for one piece of information to make it from one end of the network to the other. You can think of a network as a series of pipes, and bandwidth would be changed depending on how wide your pipe is. The wider your pipe, the more information or data you can pass through at one time, increasing your bandwidth. And that's all we did. I hope you guys have a great rest of your day, and I'll see you next class.